I'd like to provide just an introduction to chemical reactor design here by overviewing some basic ideal type reactors and indicating some important aspects. So if we look at a generic reactor where we're feeding, say, two reactants, A and B, and some fraction of them react and we make products C and D, and we're going to look at the case where there's two reactions. So A plus B can form C, or A plus 2B can form D. This might be an example of partial oxidation or partial hydrogenation reactions. And what we're assuming is that this is the desired product. So a couple important aspects about chemical reactors. The basic idea is that you want to take something that's relatively inexpensive and make something that's more expensive to justify the chemical reactor. What tends to be the overriding factor is often the selectivity, namely how often does this desired reaction occur compared to all the possible reactions. So one way that selectivity would be defined in this case would be the flow rate. So this is a molar flow rate, moles per minute or hour, for component C divided by the flow rate for C plus D, so the total products that are formed, what fraction, and it's often expressed as a percent, of course, by multiplying by 100. Well, the selectivity is really important because it affects the separation units, how much separation has to be carried out, and separation is expensive. Therefore, it affects the cost of the process. It also affects the cost by the fact that if we make a lot of product from our reactants, we make a lot of D that we can't use or sell for reasonable prices, then we're throwing away essentially a lot of our reactants. So chemical reactor design is basically looking at a chemical reactor and then doing mass balances and doing energy balances. Those are certainly the most important. Doesn't mean other things are not also used, but those are the dominating ones. And so to get an introduction, we'll just look at some of the typical ideal reactors. And sometimes these are very good approximation to real reactors. Sometimes real reactors might be combinations of ideal reactors and other things. So I've indicated here the four ideal type reactors that we often look at and that are used on large scale. One's a simple batch reactor, which certainly is just a scale up of a laboratory beaker for reaction where concentration and of course temperature can change with time. So this is not steady state. We dump in all the material at once and then carry out reaction, so a closed system. A continuous stirred reactor is really quite different. It looks like a batch reactor where we're continuously adding and removing material, and this changes things quite a bit. So one means it can be run continuously at steady state, which means the derivatives with respect to time are equal to zero. We'll talk a little more about that. And then semi-batch means a batch reactor where, for example, we might add one component like A and then continuously feed in B, and reaction now, again, is not at steady state. And then the other type of steady state reactor is where we feed in material to a tubular reactor typically, and then reaction proceeds as the material moves down the reactor. So either the reactor is filled with catalyst and that catalyzes the reaction, or the reactor is a lot hotter and that's what gets the reaction started. Again, this is steady state, which means any derivative with respect to T is equal to zero. So for these three type reactors, we assume that they're uniform spatially. Namely, there's no concentration gradient or temperature gradient across the reactor. That's not the case for the plug flow reactor. So the concentration is continuously changing as we move down the reactor. At a given point, it doesn't change with time, but it does change with location. Now, when we do these mass and energy balances, one of the critical terms that we are going to use is the rate of reaction. And for component A, this is the most common form, and this is defined as the rate of formation of component A. And so this means it has sign notation. If we're using up A, if A is our reactant, as in the example above, then R sub A is going to be less than zero. So something important to keep in mind and can sometimes be confusing, as the rate of reaction in general is not equal to the change in concentration with time. Under special circumstances that could be true, but in general it's not true. And the easiest way to visualize this is to look at the CSTR, which stands for Continuous Stirred Tank Reactor, or the Plug Flow Reactor, which is often referred to as a PFR. If we look at these two reactors, the derivatives respect to time are zero. So this means the derivative of concentration respect to time at a given location is zero. But the rate of reaction is certainly not zero if we've designed the reactor correctly. And so this is an important thing to keep in mind. The rate of reaction instead is going to be some rate constant and some concentration dependence, maybe Ca squared, or for this particular example with A and B, maybe it's first order in A and first order in B. And the units here are moles reacting per volume, say per liter per second. Could also be per weight of catalyst instead of per volume. This is an empirical term where we have to make measurements. For the simple case of a first order reaction, then the units of K would be inverse time. For the others, the units have to be such that we have, for example, moles per liter here for Ca and likewise for Cb. Then the units of K are such that units are equal on both sides of the equation. So I've listed the basic mass balances for a batch reactor, where N sub A is the number of moles of A in the reactor, V is the volume, contents of the reactor. If this is liquid phase, then the left side can be written in terms of concentration, and you can see then the reaction does not depend on the volume of the reactor in terms of what fraction is converted. For a continuous stirred tank reactor, there's a molar flow rate into the reactor, a molar flow rate out, and again a rate of reaction term. Semi-batch in general looks like a CSTR, except that the one steady state term for the number of moles in the reactor changes with time, and we may only have a flow rate in or we may have a flow rate out. And then the plug flow reactor is quite different. The change in the molar flow rate with cumulative volume as we move down the reactor. So as we have this plug, and initially and finally is our total volume, so the cumulative volume, the rate of reaction, is equal to this derivative. The final term we'll mention here is we often use conversion to determine how much is reacted, and the conversion is the flow rate coming in, a molar flow rate, minus the flow rate leaving over the flow rate coming in. This in general is not equal to the concentration difference. I say in general, but if we have constant mass density, then it is. So the final thing to mention in this introduction is the amount of reaction that occurs, or our conversion, will increase if we have longer reaction times. For example, a bigger reactor, or we leave it in a reactor longer, or typically if we raise the temperature, or since many reactions are catalytic, if we add more catalyst, we will get more reaction.